Hello everyone. In this video, we're just going to talk about coordinate vectors. So before we define a coordinate vector, this theorem is very important in leading toward that definition. So in any vector space, we have a basis if and only if every vector in the space can be expressed as a linear combination of elements from the spaces in exactly one way. Okay, so what does this mean? Like, how is this going to lead to a coordinate vector? So this basically says if I can write some v, any vector I choose, as a linear combination of elements of my basis, right? So here all of my vi's are in my basis. Then since this can only be done in exactly one way, these coefficients uniquely determine my vector v, okay? And so this is going to lead to a column vector with just these entries. We just kind of pluck off these coefficients because they are exactly what matter in defining v. Okay, so this is the idea behind the coordinate vector. So let's make this a bit more explicit. All right, so here's our setup. We'll have a basis, and here we are going to assume basically all the time that our bases are finite. So I just have finitely many vectors here. You can have an infinite number of vectors in a basis. That's just going to lead to like an infinite number of rows in your column vector that corresponds here. And that's okay. There would be at most, finitely many non-zero entries there. But we're just going to kind of simplify the situation and assume finite. And so the vector here, we're just assuming can be written as a linear combination in exactly this way. And so our notation is going to be this kind of brackets around our vector, sub b, because it is something that depends on which basis you choose. And it is exactly what I just said. So you just kind of pluck off these coefficients. They become the entries in each row of this column vector. And this here is what we would call the coordinate vector for v with respect to the basis b. And again, your choice of b is going to potentially change how this looks. And so let's look at a few examples. All right, so we're going to look actually at a few different bases here to get a better idea of what's going on. But we're going to have the same vector throughout here. So negative 2, 5 inside R2. So first we'll have our basis B1 just be the standard basis. Okay, so 1, 0, and 0, 1. So in this case, right, V is negative 2, 5. This is just negative 2 times 1, 0 plus 5 times 0, 1, right? And so this means that my coordinate vector here with respect to this basis is, well, I just pluck off these coefficients, right? So it's going to be negative 2 and then 5. Well, I just get exactly what I had back. And this is basically what you should expect when you're using the standard basis, okay? Especially in Rn, you're just going to get your vector back because we naturally write things in this way. So let's look at one that's different. So we'll actually just fix one of these and change the other. So now let's look at it. So how can I write it here? So one, you could just do some row reduction, but this is one you can eyeball because you know that the y-coordinate has to come from this second one, and that's got to be 5, right? So this has got to be 5. And so if I'm adding 5 up top, but I want to end up with negative 2, this must be negative 7. And so, right, then I'm going to get negative 7 plus 5, negative 2, 5. Okay, but then what does this mean my coordinate vector is with respect to B2? Well, I have negative 7 here, so that's my first entry, and then still 5 in the second one. So notice, right, like it depends on the basis what your coordinate vector is going to look like. So that was one we could eyeball. Let's do one that we couldn't really eyeball and see like how do we get this in general. So here's our third basis. So I'll leave it to you to check that that actually is a basis, but it should be pretty clear because It's going to be independent because they're not multiples of each other. You just have to show everything actually lies in the span. And that's actually what we want to do here, right? Because the whole goal is to say, okay, my v is negative 2, 5. How can I write this as c1 times my first one plus c2 times the second one, right? Because the second I know c1 and c2, I have my coordinate vector. So this is just an exercise in finding how it is in the span, right? So we just want to solve this linear system and find C1 and C2. And if you trust my handy dandy row echelon calculator, we end up getting this reduced form. And so C1 is going to be 1 and C2 equals 2. Let's just check that that actually works, right? So negative 2, 5 is, well, just 2, 3 plus 2 times negative 2, 1. And so we get 2 minus 4, that's negative 2. 3 plus 2 is 5. Yeah, so this checks out. And thus, my coordinate vector, right, so my negative 2, 5 in my third basis is going to be 1, 2. So let's do one more here, okay? So first of all, in the standard basis for 2 by 2 matrices, the coordinate vector for this guy would just be negative 1, 4, 3, 2, right? So we've already been kind of using this, even if we haven't called it a coordinate vector at this point. But the standard basis is what allows us to kind of very naturally throw this into column vector form. So now we have this basis down here. So actually your first exercise is check that this set above, so check that B is actually a basis. I'm claiming that it is. I want you to check. So how would we find the coordinate vector here? Well, I want to translate each of these into a column vector, right? And then see what the coefficients have to be to get me negative 1, 4, 3, 2. And so I'm just going to make columns, right? 1, 2, 0, 1, 0, negative 1, 1, 1, 1, 0, 0, negative 4, and 3, negative 5, 2, 0. And then I want to get this guy. And it turns out when you get the reduced row echelon form, you get this right here. So we have a pivot in every column, and so we can very quickly see, right, that C1 is 5, C2 is 9, C3 is 3, and C4 is negative 3. And so this means that my coordinate vector for this guy is going to be 5, 9, 3, negative 3. Okay? Okay, and so now for your second exercise, I want you to find the coordinate vector for the polynomial x squared minus 3x plus 2 for this basis of P2. So 2 minus x, x squared plus x, and 3 minus x squared. Thank you for watching.